Hello everyone, welcome on our YouTube channel Physics Made Easy Kota. This video lecture is related to the chapter Magnetism and Matter, and this is the second part of this video lecture. My name is Diljit Kaur and I am going to discuss a few important contents regarding this chapter. Have a look on these contents. We are going to discuss all these contents one by one. Firstly, we are going to understand the difference between the magnetic field lines and the electric field lines. Electric field lines start from the positive point charge and end on negative point charge. They do not form closed loop, whereas magnetic field lines start from north pole and end on south pole outside the bar magnet, and magnetic field lines are from south to north pole inside the bar magnet. Hence, magnetic field lines form closed loop. There are some properties of the magnetic field lines. The magnetic field lines always form a closed loop. The tangent to the field line at a given point represents the direction of the net magnetic field at that point. Closer the field line, stronger is the magnetic field. Magnetic field lines never intersect each other because at the intersection there will be two tangents giving two different direction of the field at that respective point, and which is not possible. Bar magnet act or behave as a solenoid. It is also called as bar magnet as the equivalent current carrying solenoid. The magnetic field lines of a bar magnet resembles with the magnetic field lines of a current carrying solenoid. Magnetic field line of a solenoid and a bar magnet can be practically found to be same. If a magnetic needle is brought near a current carrying solenoid and then near a bar magnet, it is observed that deflection of needle is similar in both cases. If we cut a solenoid into two pieces like a bar magnet, we get two small solenoids of weaker strength. This shows that a bar magnet behaves as a solenoid. A bar magnet can also be considered to be consisting of many circulating currents, just like a solenoid. Axial field of a solenoid is similar to that of a bar magnet, and we get an expression for the magnetic field for the axial field of a solenoid is mu naught upon 4 pi 2m divided by r cube. This expression of the magnetic field is same as in the case of a bar magnet. So from that we conclude that solenoid and a bar magnet produce similar magnetic field and they have same magnetic moments. Magnetic dipole. It consists of a pair of magnetic poles of equal and opposite strength separated by a small distance. For example, bar magnet. Bar magnet act as a magnetic dipole. Another example that come in our mind is magnetic needle. Current carrying solenoid also behave as a magnetic dipole. Magnetic dipole moment. It is represented by using the symbol small m, that is equal to qm multiplied by 2l. Here q represent the pole strength of either pole and 2l is the distance between the magnetic poles. Magnetic dipole moment is a vector quantity because the magnetic length is directed from the north pole to the south pole. So we can say that the direction of magnetic dipole movement is from south to north pole of a magnetic dipole. Consider a bar magnet or a magnetic dipole in a uniform magnetic field, and the angle between the direction of magnetic dipole movement and the magnetic field is taken as theta as shown in the figure. Let magnetic length of a magnet is 2L, pole strength is represented by Qm, and of course the force acting on both the poles when they are placed in the magnetic field. So the force acting on the north pole is Qm into B, and this is along the direction of the magnetic field, whereas the force acting on the south pole is opposite to the direction of the magnetic field. So these forces are equal but in the opposite direction, so they form a couple which tends to rotate the magnet in the direction of magnetic field. Hence, because of this, bar magnet experience a torque and it tends to rotate, and the torque is acting on the bar magnet is represented by the relation magnitude of force multiplied by the perpendicular distance between the force. As the magnitude of force is same for both the poles, so this is equal to qm into b. Perpendicular distance is represented by doing some construction that is represented by Zn. Then put the value of the Zn by using the trigonometry function sin theta. We get a expression qmb multiplied by 2l sin theta. We know that qm into 2l is equal to the small m, that is a magnetic dipole moment. So there is a change in the expression, and the final expression for the torque is mb sin theta. We can also represent the torque in the vector form, that is tau vector is equal to m vector cross b vector. Now we are going to learn about the expression for magnetic field strength at a point on the axial line and the equatorial line. First of all, what is the axial line and what is the equatorial line? I am going to explain one by one. The first axial line. Axial line is the line that join the south and the north pole of a magnet and extended on either side. This line is represented by the straight line that passing through the center and extended on the either sides of the pole. Whereas the equatorial line is a line which passes through the center of the bar magnet and perpendicular to the length of the bar magnet. Now we are going to understand the magnetic field intensity on a point on the axial line of a bar magnet. Now let us consider O be the center of a bar magnet, and this bar magnet having the magnetic length 2L. Now consider a point P on the axial line of a bar magnet at a distance small r from the center O of the bar magnet. Assume Qm represent the pole strength of each pole of a magnet. Let a unit north pole be placed at a point capital P. Capital P is the point where we are going to calculate the magnetic field intensity. Assume that the presence of the unit north pole at point capital P does not affect the magnetic field at point capital P due to the bar magnet. Now the magnetic field intensity at a point P due to north pole of a bar magnet is equal to the force experienced by the unit north pole at a P due to the north pole of the magnet, and this force is acting along the x-axis, so we represent the direction by using I cap. Similarly, we can also calculate the magnetic field intensity at a point P due to the south pole of the magnet, and the direction is along x dash, that is along the negative x direction, so this is represented by minus I cap. So we can calculate the net magnetic field, that is by the addition of the, that is by a vector addition of v1 vector plus b2 vector. After solving, we can also get the expression for the magnetic dipole, and we can replace the qm into 2l by the small m that represent the dipole moment. Then the final expression we get is mu naught upon 4 pi 2mr divided by r square minus l square whole complete square into I cap. I cap represent the direction. Now for the equatorial line, consider the point P represented on the equatorial line of a bar magnet, which is at a distance small r from the center of a bar magnet. Now we can calculate the magnetic field at this point due to north pole and the south pole of a bar magnet, and that is represented by equation number 1 and 2. We observe that the point P is under the effect of both the B1 and B2, and for symmetry we can calculate the net magnetic field at point P. Then after solving, we can get the expression in terms of the magnetic moment, that is represented by capital M. For the special case, if a bar magnet is taken of the smaller length, then again the expression got changed, because in this case the capital R become very greater than the small l, that is the distance between either pole and the center of the bar magnet become very small, and it get reduce. So we can easily ignore the small l in the expression, and we get the new expression, that is mu naught upon 4 pi m divided by r cube. Now you can easily observe that there are the various physical quantities, and they have the respective formulas in the magnetism and the electrostatic, and we can see there is some kind of the similarities in both the formulas, so that they can easy to learn, or we can easy to cram them for the numerical purpose. Potential energy or a stored energy of a magnetic dipole or a bar magnet is possible whenever we do a work to rotate a magnetic dipole in a uniform magnetic field. Whenever a dipole gets rotated by the angle theta, then it experiences a torque. Torque is equal to mb sine theta. And if we assume that we rotate a dipole through the small angle, then the small work has to be done in rotating it. That work is equal to dw. It is given by the tau d theta. Put the value of the tau, and that is expression for the small work done in displacing a magnetic dipole or a bar magnet by the small angle d theta. Then we want to calculate the complete work done. For this we do the integration by assuming the condition, let the dipole get rotated from the angle theta 1 to theta 2, and we get the final expression of the work done that act as a potential energy. Now this final expression is mb multiplied by cos theta 1 minus cos theta 2. Now if we assume that the theta 1 is equal to 90 degree and theta 2 is equal to theta, then we have the final expression of the work done or the potential energy is minus m vector dot b vector. Again we can discuss some special cases on this final expression. There are the two special cases: unstable equilibrium and stable equilibrium. Unstable equilibrium means it has a maximum potential energy, like it become unstable, store a maximum amount of the energy, try to release it. In this condition is possible only when m vector and b vector are antiparallel. For the stable equilibrium means stability deals with a minimum potential energy, and this is only possible when m vector and b vector are parallel to each other.